Welcome back to the Deep Dive. Today we're tackling a problem that is, well, it's arguably the biggest computational roadblock for large language models right now.
Context length.
Exactly. Context length. I mean, if you want an LLM to read a whole book or maybe a massive legal document, we're talking million token inputs, the system just grinds to a halt.
It creates this massive immediate challenge for computation for memory.
So the industry's main approach to this has been something called context compression. Basically, how do we squeeze that entire book into a dense, manageable packet without, losing the important stuff?
And that's our mission for this deep dive. We're going to analyze two really advanced compression strategies. First, there's the one that was the previous state-of-the-art, Contexts Optical Compression, or DeepSeek-OCR.
Okay.
And second, the new breakthrough, the thing that really changes the game, Context Cascade Compression, or C3. And we're going to get into the weeds on this, focusing heavily on the quantitative metrics.
The numbers.
The math. How high can we push that compression ratio while still getting, almost perfect reconstruction?
Well, let's unpack that. But before we get to the solutions, we have to understand the problem.
Yeah.
The mathematical bottleneck. Why can't you just feed a billion tokens into an LLM?
The problem is baked right into the transformer architecture itself. Specifically, the self-attention mechanism.
Ah, okay.
If you remember your complexity theory, it has what we call quadratic computational and memory complexity. So that's with respect to the input sequence length, n.
We call that O of n squared, right?
Exactly, O and $2. And what that means in practice is, well, it's a disaster. If you double the length of your document, the compute power you need doesn't just double.
It quadruples.
It quadruples. This quadratic explosion just makes processing a long context insanely expensive. It creates a hard ceiling.
We have seen other attempts to get around this, haven't we? Things like efficient attention, sparse attention, that kind of thing.
We have, yeah. Methods like sparse or linear attention try to, let's say, lower that exponent, maybe get it closer to 1. But they don't solve the fundamental problem, which is that the token count, n, is still massive.
And what about RAG?
Retrieval augmented generation, RE, is inherently lossy. It's a form of compression, I suppose, but it's basically having another system guess what's relevant before the main LLM even sees the context.
Okay, so that brings us to the first big attempt, DeepSeek-OCR. It tried to get around this whole N token problem by, changing the data type completely.
Exactly. It shifted modalities. DeepSeek-OCR pioneered this idea of context optical compression. It was a really clever idea. Instead of treating text as, a sequence of symbols.
It treats it as an image.
As a visual signal, yes.
Yeah.
The pipeline is pretty wild. You render the text into an image, like a high-res screenshot of the page. Then a visual model, like a vision transformer, encodes that image into these compressed visual latent tokens.
And those are what you feed to the LLM.
That's what you feed to the LLM.
So numerically, what did that get us?
Yeah, it was a big step. DeepSeek-OCR could reliably hit a 10x compression rate. So 1,000 text tokens could be represented by 100 visual tokens, and it would maintain about 97% decoding accuracy.
But there was a catch.
There was a big catch. When you tried to push it, say, towards 20x compression, 1,000 tokens down to 50, its accuracy just fell off a cliff, down to 60%. The visual approach just can't handle that kind of density without major distortion.
Which is the perfect setup for this new method. So if DeepSeek-OCR is like trying to compress a novel by taking a single kind of blurry photo of it, what is C3, Context Cascade Compression, doing differently?
C3 starts by asking a more fundamental question. Was the success of the optical method really about turning text into an image? Or was it just because latent tokens, these dense continuous vectors, are just a much more efficient way to encode information than discrete text tokens?
So C3 gets rid of the visual middleman.
It gets rid of all the visual noise. Yeah, it's a test of the pure limits of text-to-latent compression.
Can you walk us through the architecture? I'm hearing cascade, which suggests there's more than one model at play.
That's right. It's a pure text, very streamlined pipeline. You go from text to text tokens, then into a small LLM that acts as an encoder.
Okay.
That encoder produces these textual latent tokens, which then go into a large LLM that acts as the decoder. Think of the encoder as a super efficient summarizer. They used a 1.5 billion parameter model for this. And the decoder's job is to turn that summary back into the original text. For that, they used a 3 billion parameter model.
But how does it handle the compression itself? How does it always output a fixed number of tokens, no matter how long the input is?
This is where the architectural math gets really elegant. It uses a concept called the context query.
The context query.
Right. So imagine your input context, thousands of tokens long. What you do is you stick a short, fixed set of learnable embeddings onto the end of it. This is your context query.
So it's like a special instruction set for the model.
You can think of it that way. Mathematically, it's a trainable tensor. Let's call it Q. If we decide we want our compressed output to be, say, 64 tokens long, then this tensor Q has a shape of n by d, where n is 64.
And D is just the model's internal dimension.
Exactly. So the encoder processes the whole thing, the original text plus these 64 query embeddings, using standard attention. But here's the magic. We only look at the final hidden states that correspond to the positions of those 64 query tokens.
Ah, so you just throw the rest away?
You throw the rest away. So it doesn't matter if the input was 500 tokens or 5,000. The output is always precisely 64 latent tokens, a perfectly fixed-length, dense vector.
Okay, so structurally, this means C3 is forcing the encoder, using this mathematical trick, to distill all the semantic meaning from a super long input into a tiny fixed-length code. It's a pure semantic autoencoder. No visual mess.
Precisely. We've eliminated all those variables like document layout, font size, image blurring. We're now measuring the pure ability of a transformer to perform semantic distillation. And that sets us up for some much, much higher compression limits.
And now we get to the numbers. This is where the story really flips. We're looking at the Fox benchmark for accuracy.
Yeah.
Let's start with that 64 latent token setting where the optical method started to fall apart.
Right. So if you look at DeepSeek-OCR at around 13x compression, that's about 800 to 900 input tokens compressed to 64. Its precision had already dropped to 83.8%.
It's already struggling.
It's struggling. Even moderate pressure was causing significant fidelity problems in that visual domain.
Okay, and this is where it gets really incredible. Let's push both of them to the absolute limit for this 64 token bucket. We're talking about compressing around 1,300 text tokens down to just 64. That's a nearly 20x compression ratio.
An aggressive ratio.
Right.
And C3. It achieves an exceptional precision of 98.4%. It barely even notices the pressure.
And DeepSeek-OCR.
This is the definitive moment. DeepSeek-OCR, trying that exact same compression, just plummets. It delivers only 59.1% precision. It's basically useless at that point. The gap is enormous. It proves that this direct text-to-latent mechanism is just fundamentally better at preserving meaning than trying to send it through a pixel-based representation.
And the reason, as you said, is that it's immune to those visual problems.
Mm-hmm.
You don't have to worry if a complex table is blurring into unreadable mush when you squeeze it down. C3 just focuses on the meaning.
Exactly. It's using the power of a pre-trained language model, which already gets text semantics, to do the job, rather than forcing that meaning through a lossy visual layer.
Okay, so to really probe the limits, the researchers pushed it even harder. They tested compressing down to just 32 latent tokens.
Cutting the available information slots in half.
How did it do under that kind of extreme stress?
I mean, the results really challenge what we thought we knew about information density in LLMs. Even when you're compressing, say, 1,000 tokens into those 32 slots, that's a staggering 30x ratio C3, maintains 98.8% precision.
That's unbelievable. It's converting over 30 text tokens into a single latent token and still gets it almost perfectly right.
It's incredible fidelity.
So they went for the absolute max, 1,200 to 1,300 tokens, squeezed into just 32 latent tokens. We're at nearly 40x compression. Did they finally break it?
Not really. Even at almost 40x, C3 is still holding at 93.3% precision. The optical method failed at less than half that rate. It confirms the whole hypothesis. Direct semantic distillation sets a new and potentially very, very high upper bound for compression.
And beyond just the raw numbers, the qualitative studies gave some fascinating, almost human-level insights. C3 showed it could perfectly reconstruct really messy, text-like English prose mixed with random, meaningless characters.
Or even structurally disordered classical Chinese, yeah. It not only reconstructs the text, it cleans up the mess. It's performing deep semantic organization, not just, token reduction.
So it's a noise-resistant autoencoder.
A very sophisticated one. But if we want to understand its limits, we have to look at how it fails when you push it to the absolute breaking point.
And that's where things get really interesting.
That's where it gets fascinating. Because the failure mechanism is completely different. Unlike the optical method, which gives you a uniform degradation like the whole text just gets blurry at once, C3 shows a very specific pattern.
Which is?
Sequential information loss. When errors finally start to happen, they are overwhelmingly concentrated at the end of the original text.
Wow. Okay, that is a powerful connection. Because that sounds exactly like the decay of human memory.
It is. It's the primacy effect. We remember things we heard first with higher fidelity, and the details we absorb later, especially when we're overloaded, are the first to go.
So C3 is naturally prioritizing the beginning of the information stream, and the loss happens progressively at the end.
And that's profoundly different from a diffuse, chaotic loss. It means the failure mode is predictable. If you know where the errors are likely to be, you can manage the system so much better.
That has huge strategic implications. You know where the fidelity is highest, and you know where you might need to, say, supplement with some other retrieval method. It's a manageable error mechanism.
Exactly. It's not just a technical breakthrough, it's a hint about how information overload could be handled in any complex system, whether it's artificial or biological.
So to summarize the findings of this deep dive then, we've completely moved the goalposts. We've gone from this indirect optical method that struggles past 10x to C3, a direct mathematical autoencoder that maintains stellar precision all the way up to 40x.
The conclusion is pretty clear. By leveraging the LLM's own innate semantic understanding, C3 sets a new state of the art and dramatically reduces the resource drain of processing these ultra-long contexts.
And the practical applications feel huge and immediate. This gives us a clear path for managing information flow in these advanced AI systems. It means you can now efficiently handle, I don't know, a 200,000 token legal brief by reducing it to 5,000 latent tokens.
Which significantly lowers the computational cost for both training and inference. It's a big deal for enterprise use.
And beyond that, C3 isn't just an input filter, is it? It could be a foundational component for next-gen models, like the fusion language models, that need these high-quality, fixed-length representations to work.
Which brings us to a final, really important question for future research. If this information loss pattern, this explicit analogy to human memory, where things fade sequentially from the end, if that's an emergent property of efficient semantic compression,
Then what does that mean?
does optimizing for this specific kind of sequential fidelity loss offer a new, more biologically plausible path for building massive and efficient AI memory systems? What if the key to perfect AI recall is actually learning to forget just like a human does?